Al, and good afternoon to everyone. I'm glad you were able to make it. This is one of my favorite lectures. I've given this numerous times, both when I was working with ExxonMobil and since then. And as the slide says, we're going to look at well data and how it relates to seismic data. We'll see this figure later in the lecture. But we have a piece of seismic. It's been cut where there's a well and moved away, so we have a little bit of space. And then this wiggle is a modeled or synthetic trace that has been generated by using well data. And so what we'll do is use that modeled trace, which is linked to the well geology, in order to tie or relate things that we see in the well to peaks and troughs that we see on the seismic data. So that's a little preview. So I'll talk about what a well seismic tie is, do a quick comparison of well data and seismic data, talk about how we generate this modeled or synthetic trace. I'll show you the workflow that is typically used, how we tie the modeled trace to the real seismic data, and then a chart that tells us what constitutes a good well seismic tie. So a well seismic tie, whenever we have well data and we have seismic data, we would like to relate the two of them. And so we have well A here, and we have the top of a sand. We'll call it sand A. It's at a certain depth in meters. And here's where the well is located on the seismic line. And so we would like to know what event on the seismic, a peak or a trough or a zero crossing, corresponds to that top of sand. The top of sand we have in depth in meters, or it could be in feet. And typically our seismic is in two-way travel time, either in seconds or what is more common with seismic is to talk about milliseconds. So there's two main issues in trying to relate well data and seismic data. One is the change in scale from depth in feet or meters for the well data versus two-way travel time, which is the basic measurements we do with seismic. We can do extensive processing to convert the wiggle trace from two-way time vertical axis to depth. The other thing is that the seismic pulse, the energy wavefront that's going down, that has a certain time duration, a certain characteristic, and that limits resolution. And so we would like to know how those limitations, because of a non-infinitely small pulse duration, impacts the appearance of the seismic wiggles. So our goal, we want to be able to relate features from the well data. Might be formation tops, it might be the position of a fault, it might be where we have chord part of the section. And we want to relate those to peaks or troughs on the seismic line that passes through the well location or close to the well location. If we have 3D seismic, we can get a line right through the well, and the well may not be straight vertical. It could be deviated. With a 3D data set, we can extract a seismic line that follows that well path. If we have a 2D survey, then our well might be on one of the 2D lines or might be close to one of them, but not actually on it. Similarly, we may see something of interest on the seismic that we may want to try to relate back to the well data. So perhaps we see a very large amplitude reflector. We could ask the question, what is that related to in terms of the well information? So we can go from the well to the seismic, which is probably the more common task, but we can also start with the seismic and tie it back to the well data. In order to do the tie or the relationships, we need to have some way to convert from depth to time if we're going well to seismic, or time to depth if we're going from the seismic to the well data. We also want to model how individual wavelets caused by the various impedance boundaries or reflection coefficients combine to give us the response that we see on the model trace and also on the real seismic traces. So very briefly on well data, we sample points along the well bore. That could be a pure vertical path or it could be a deviated path. If we have a sonic log, the frequencies that we are using to get sonic data is 10 to 20,000 hertz, much higher than the actual seismic. We have very good vertical and horizontal resolution. Things that we measure with well data, we can get the vertical velocity if we have a sonic log. We can get density. There's a couple of different logs we can use to get the density of the rocks. We can get resistivity, and we can get other rock and fluid properties. And all of these measurements are depth along the well path, either in feet or meters. And I'll talk a little bit more about the depth measurements in a minute. With seismic, we're able to sample areas if it's a 2D survey or actual volumes of the subsurface if it's 3D data. Seismic frequencies are much lower than what we use with the sonic log. They're in the 5 to 100 hertz. Vertical resolution depends on the depth that we're talking about and what the velocities of the rocks are, but the vertical resolution for really good data might be 15 meters, could be 100 meters, could be even 200 meters of resolution. Horizontal resolution, that can be on the order of a couple hundred meters to a kilometer or more. With seismic, we measure amplitude, we measure the phase of the wavelet, we can measure how continuous a reflector is, we can generate or estimate from the seismic data set horizontal and vertical velocities. And our basic measurement with seismic data is time, two-way travel time, and again, usually we relate that to milliseconds. So how might 100 meters of the well appear on the seismic? How many milliseconds would that represent? And that will differ as we go from a shallow part of the section or well to a deeper part of the section or well. With our well data, there's a rotating table here. There's a piece of that that's called the Kelly bushing, and almost all well data I have ever seen, the depths are relative to the elevation. And so the measurement is depth or meters down from that bushing. And if it is a deviated well, as shown here, the measured depth will be along the deviation path, and what we would really like is true vertical depth. We have instruments that tell us what the actual well path is, and so with a directional survey, we can convert any measured depth on the log to a true vertical depth. With the seismic, we have a shot, the energy goes down, hits an interface, and comes back up to the receiver. One of the goals of seismic data processing is to try to represent that as if the energy went straight down and went straight back up. And the surface elevation, we will know. There is something that we call the seismic reference level or seismic reference datum, and all the seismic in a particular survey will have a single value for that. If we are acquiring data at or very close to sea level would be the reference datum. But if we're acquiring data near Denver, Colorado, which is at an elevation of 5,200 feet, our reference level might be 5,500 feet or it might be 5,000 feet. It would not be sea level. So we have to remember that the two data sets, the well data set, the seismic data set, may have different reference levels. One thing that we can get to help with our time to depth relationship is what is called a check shot survey. Another name for check shot data is a velocity survey. And if we have a supersaturation of data, we call that a vertical seismic profile. So it allows us to relate well depth in feet or meters to seismic tie. And so looking at the diagram on the right, here we have a truck that's going to lower a geophone down in the borehole. We know what that depth is by how much cable has been played out. We'll have a seismic shot or vibration point close to the well bore. We know when that shot is fired, and then we'll measure the time one way for the energy to get down to this level. And so let's say this borehole is at 1,000 feet below surface. We now know that 1,000 feet, it takes so many milliseconds for the energy to reach that. And so we have a direct tie between a depth measurement and a time measurement. For a check shot survey, typically we'll have maybe 20 or 30 depths at which the borehole geophone is positioned, and we have a shot fired. With a VSP, we might have 1,000 depths at which the geophone is positioned. So this allows us to figure out the relationship between one-way travel time and depths. What we need to determine is the start time for the top of the wells, because typically our shallowest geophone is not at the surface, and we may have to calibrate the relationship between the well depths and the times using the sonic log. So to generate a modeled synthetic trace, here we have well A. This is the lithology shale on top of sand. This might be what the velocity data looks like. Shales in this instance are slightly higher velocity than the sands. The density is a little higher in the shales, a little lower in the sand. That might be because we have gas in the sand. And if we multiply velocity times density, we can compute what the impedance log would look like. Typically, we'll block the logs. We'll take out the high frequency oscillations so that we have fewer reflection coefficients to keep track of. I'll talk about this. That blocking can be done by hand, or we can have the computer do that for us. Then we calculate reflection coefficients, and back in lecture 3 or 4, I talked about this equation, the impedance below interface minus the impedance above divided by the impedance below plus the impedance above. And so we can represent the subsurface as a series of reflection coefficients. The spikes going to the left would be decreases in impedance, such as this big decrease. Spikes to the right are increases in impedance, and you can see this big step down in impedance gives me a long spike towards the left. The smaller steps in impedance give me shorter reflection coefficients. So I can calculate not only the sense of impedance change, increasing or decreasing, but also how much does it change, a tiny bit or a moderate amount or a relatively large amount. If I know what the seismic pulse or wavelet is, or I can approximate that, this is a zero phase pulse that I'm going to assume is appropriate for my data set. I can use a mathematical operation called convolution to convolve this waveform with each one of the reflection coefficients, generate what each individual response would be, and then sum them up so that I get the modeled response that would include both constructive and destructive interference effects if the reflection coefficients are close together. So the reason I do the blocking is so that I have 15 or 20 reflection coefficients in my zone of interest instead of 100 very small magnitude, and then I can't see what the major cause for some of the peaks and troughs on the model trace look like. So if I have the top of my sand, it's a big decrease in impedance, a negative reflection coefficient. This is my wavelet. In this series of wavelets, when I do the convolution and the summation, I still get a big trough associated with the top of the A sand. And so if I want to map the top of the A sand, I would pick this trough and snap my horizon to the most negative number. Let me talk a little bit about the workflow. Our input data, we need some well data. In particular, we want the sonic log. We would like the density log as well if it's available. And if it's not a vertical hole, we need the deviation survey so we know what the actual well bore path has been. With the seismic data, we would like a line through the well, if possible, or close to the well if we're dealing with a 2D data set and the well was not drilled on one of the available lines. And we could use either the full stack data or we could use a near stack, a partial stack of just low angles of incidence. We may have to do some log editing, taking out some of the problems associated with wells such as washouts, where the casing shoes might be, some errors perhaps in deriving the sonic data like cycle skips, accounting for areas where the drilling fluid has entered into the formation and we have to take that into account. And we could have a stuck tool so that the same interval is being recorded several times on the log. We can do the blocking. That is an optional step. We can do it manually. When I started back in 1977, that's what we had to do. We had to use pencils and mark things and then digitize it. We can also have the computer do that. And if we ask the computer to do that, usually what we give as controlling factors is what's the minimum bed thickness that I want to consider. I don't want to consider beds that are smaller than 10 meters as an example. And then what percentage change in impedance do we want to capture? So typically we ignore things that are less than about 0.5% to maybe 1% change in impedance. We need some time to depth data to calibrate against. The vertical seismic profile is the most dense sampling of time and depth, using many locations or depths at which the well bore geophone is positioned. Check shots, we have fewer control points, but it still gives us good data. And if we don't have a VSP or a check shot, then what we'll use is the velocities that the seismic data processors develop in order to stack their data. We also need the wavelet or the seismic pulse. Analytic, we can define a shape and then what the central frequency is. The common shape that I have always used is called a Ricker wavelet. And so if I say I want to have a shape that is the Ricker wavelet, and I want the central frequency to be 28 hertz, those two parameters define what my wavelet will be. The other option, instead of using an analytic defined shape, we can use statistics from the seismic. We can define a window around our zone of interest or our depth of interest, and then have the computer extract using statistics what the wavelet shape probably looks like. When we do this extraction, it is assumed that the seismic data we are dealing with is zero phase data, and so if we do not have zero phase data, we may have to do some work in order to get it to zero phase. And then we can generate our modeled trace or our synthetic trace. We use the mathematical procedure called convolution. We have our reflection coefficients from our sonic and density logs. We have our wavelet, either an analytical or an extracted wavelet. The software can handle multiples, and it can also handle amplitude versus offset effects. So the analytic wavelet, we need to know what the phase of the wavelet is. Is it minimum phase or is it zero phase? And so here I have a sample increase in impedance that would lead to a positive reflection coefficient. If I have zero phase data, then I would have a little precursor peak, a big trough, and a post-cursor peak. And so if I understand that my data is zero phase, I can either try to extract the wavelet, or I could say, I think I'll use a Ricker shape, and I estimate that the central frequency is 38 hertz, or whatever it might be. If it's minimum phase, we can also input into the modeling software what that minimum phase pulse looks like. And so, as I mentioned, if it's zero phase, we can say, I want a Ricker-shaped wavelet. I want it to have a central frequency of 25 hertz. This is an example of a synthetic derived for the Barracuda 1 well. If you've been working some of the exercises that go along with the lectures, you'll be familiar with this data set from Australia, from the Gippsland Basin. The tracks are numbered up here, 1 through 10. Track 1 is the scale. On the left side is depth in milliseconds, so here's 0.9 seconds to a travel time. And then on the right is depth in meters, so here's 1,000 meters, 1,100 meters. In track 2, the purple is the gamma ray, and that's a log that we would use to try to separate the shales from the sands. Top of the sand is right about here, where the gamma ray jumps towards the left. And the blue curve here is the caliper that measures how wide the wellbore is. This is the information that we would use to decide if we have some washout zones that we have to correct. Track 3 is the sonic data, delta T or DT. It is in milliseconds per meter. So it's the inverse of velocity. The blue is the raw curve with the high frequency. And if you look closely, you can see there's an orange curve that's more blocked. It's taken out some of that high frequency. Track 4 is the density. We don't have density data for this portion of the well. We do have density down here. There was probably a run change, so they probably drilled to this depth, then logged from here up, then continued to drill and logged the next section. And either this log data is missing, or maybe it was never collected, or various other reasons might exist why we don't have that. Again, the green is the high frequency raw data, and then there's an orange curve that's more blocked, and that's the block curve. And then track 5 is the acoustic impedance. That's simply the sonic times the density. Again, the thicker red line is using all of the data. The thinner red line is the blocked data. Here are some formation markers. This is the top of the lake entrance formation. This is the top Latrobe unconformity. This is the top of the reservoir, the top of the coarse clastics, which corresponds roughly with where the gamma ray decreases. This is a sequence boundary that the seismic interpreters had carried, the gold sequence boundary. Track 7 has the reflection coefficients. Again, spikes either to the left of 0 or to the right. If it's to the left, it's a decrease in impedance. If it's to the right, it's an increase. If it's a small spike, it's a small change in impedance. If it's a larger spike, it's a bigger change in impedance. We have something going on here where we have a high velocity and a high density, and so we get a big positive followed by a big negative with interference effects. Most of that is going to get canceled out. Track 8 is my wavelet. This is what an increase in impedance, positive reflection coefficient would generate. So it's a zero phase pulse in which an increase in impedance would be marked by a central trough. So this is, I believe, SEG reverse. It's a Ricker wavelet, and 22 says to me that that wavelet has a central frequency of 22 hertz. We convolve this wavelet by this series of reflection coefficients, and we get track 9, which is the synthetic or the model trace, and we have replicated the model trace 3 times so it looks more like a piece of seismic. And this is the trace then will compare to the real data. And then track 10, here's a piece of the real seismic in the black and white that goes through the well location. In red is this synthetic. The color was changed so we can tell what's the model and what's real. When I was doing this, I didn't know what the best central frequency was, and I tweaked it until the zero crossing black to white or red to white, and this zero crossing white to black or white to red had the right time duration. And so for my area of interest around the top of Latrobe, this seems to be a reasonable well tie. I have a high amplitude peak here. I have a high amplitude trough. I have a modeled peak that's a little less amplitude than the real data, but for my purposes, that's a reasonably good tie. So once we have the synthetic or model trace, what we want to do is splice it into the real seismic. So this is a different piece of seismic, a different well, but here is the model trace. It would be positioned where the white gap is, and so I'll copy that over. And in this case, the reds would be the peaks, the blacks would be the troughs, a big black trace, and a big red on the real data. That looks like a reasonable tie. Kind of a lower amplitude zone, that seems reasonable. A little higher amplitude up here, kind of one peak and another peak, one peak on the model trace, another peak here. And so this seems to be a fairly reasonable tie in this particular part of the well. So let me show you one more slide. What is a good tie? It depends on what your needs are, and those needs change with your business stage. And so if you're very early in the business stage, you're trying to figure out if you should bid on some blocks or where you might want to drill your first well, you're doing regional mapping, you just need the model trace to match the real data within a few cycles. You can live with poor to fair quality seismic, and so you can map regional flooding surfaces or regional unconformities. If you're in the exploration stage and you're starting to get serious about drilling one or more wells, then you usually want the accuracy to be within a half of a cycle. A cycle would be a peak or a trough. Usually you need seismic data that has at least good data quality. And then you can compare leads to nearby wells if you have local wells to tie back to. In the exploitation stage, field development, field production, you want the synthetic to match not just peaks and troughs, but the actual characteristics of the peaks and the troughs. You need very good to excellent seismic data, and then you can start to try to use calibration of seismic attributes to make predictions, and you can also use the seismic processing called seismic inversion to try to go from the seismic wiggles to information about the rock and fluid properties along the seismic line. So we have a few minutes, so I put in the introduction to the exercise that goes with this lecture, exercise 15, well seismic ties. So you're going to have 4 horizons, and you want to match or correlate those horizons to portions of the seismic trace. So this is the well that you have, Southland Paper Mill number 1. We have velocity, we have density, we have impedance, we have the reflection coefficients. These are all the wavelets, individual wavelets from negative reflection coefficients. These are all the wavelets from positive, and if you sum them all together, you get the modeled or the composite trace. And we have 4 formation tops. The top of the Austin Chalk is here. The top of the Eagleford Shale is at this depth. The top of the Woodbine Sand is at this depth, and the top of the Buda Limestone is at this depth. And you'll notice that this well appears to have intersected the top of the Buda and has drilled within the Buda, let's see, it looks like about 300 or 400 feet. So here is the seismic line. This is the well that we were talking about, Southland Paper Mill number 1. It's a pure vertical well. And so we can put our model trace, which is the red, on top of it. Our zone of interest is down there, so let's zoom in on that. And so here's the real seismic data, black and white, a little grainy. The red is the model trace. And so this peak here seems to correspond to this peak here. And having worked this data, I happen to know that that's the top of the Buda Limestone. So now I know that if I have zero phase data, I would map the white, I would map the black right through here and correlate that around as the top of the Buda Limestone. And similarly, you can do the same thing for the top of the Austin Chalk, the top of the Eagleford Shale, and the top of the Woodbine Sand. So if this sounds like something interesting and you'd like to try your hand at it, I'd invite you to work on the exercise 15 that's available within the IRIS data set or course that we're working through. So that finishes our prepared statements for the well seismic tie. Next week, Tuesday, we'll talk about seismic acquisition at a very high level. Well, certainly there is more information than I can squeeze into a 35 or 40-minute lecture. And then Thursday, again, a very high level on seismic data processing. So I will turn it back to Dr. Sumi and see if there are some questions.
Great, thank you. Dominic Naday writes in, has there been a situation where there is no match between seismic and well logs?
Yes, I've been privileged to struggle with quite a few well seismic ties. And sometimes, especially if the well data and the seismic data are fairly good quality, the ties are not too difficult to make. But if we get in areas where the seismic has a lot of problems and the well data has a lot of problems, if we don't have any check shot data or VSP data to calibrate with, it can be very difficult. So you work with what you have, and you need to come up with some answers. So I think in almost every case, I was able to get a well seismic tie that I could live with, maybe not real comfortably, but when you're presenting information to supervisors or managers or vice presidents, usually they have gone through this thing much earlier in their career doing well seismic ties, and so they know some of the pluses and minuses, some of the pitfalls. And based on the seismic data quality that they see, they can realize, well, this is an area where my well ties are maybe not going to be quite as good as we would like.
Great, thanks. Ramya asks, what about extracting wavelet from well? Is it advisable to use in any step of well to seismic tie?
Yes, some people will filter the well data I would recommend that if you have velocity and density logs, that you compute the impedance computed log, and then you can filter that log so that it only has the same frequency content that your seismic data is. So the line that I had up there, the frequency content here might be 10 to 35 or 40 hertz. I could filter the impedance log for that frequency range, and then use that information as a way to try to relate the well data and the seismic data.
Great. Ahmad asks, if we are to tie a well to a 2D seismic data line, what level of confidence do we have if there is no line running through the well location, or the line that runs through the well is of poor quality? So it's a level of confidence question.
Right. I think what you have to do is you have to attempt to do the well seismic data, well seismic tie, and then see what quality of a match there is. One of the things that sometimes people will do is they'll take the shortest distance from the well to the nearest line, and if you are in an area where there is structural dip, I would actually project the well along the structural dip orientation to the seismic line. So it might not be the shortest distance, but it should kind of compensate, if you will, for the regional structural dip. If you have several different vintages of 2D seismic data, and the closest well is poor quality, if it's not too far to project, you could use another line that has better seismic data quality. So on this slide, you can see that this well is not on the line. It's been projected 3,000 feet. And this well is being projected 500 feet to get to the seismic line. So this is kind of the distances that we sometimes have to do, half a mile to maybe even a mile, to project the well into the seismic line. That brings up an important point. If you are proposing to drill a well and you only have 2D seismic data, it is very wise to position the well along one of your seismic lines, as opposed to a position where you're going to have to project a long way back to the seismic.
Great. What is the advantage or disadvantage of using one type of wavelet? Like, why use a zero or minimum wavelet, I think, for example?
Well, you would like to use the wavelet phase that corresponds to what your seismic data is. The line on the screen right now, I would comfortably guess is minimum phase. And so I would probably want to model this using a minimum phase pulse. The other thing that I'll mention is that we typically don't do a single model. If I have a zone of interest down here, I might use a minimum phase pulse with maybe a 15 or 18 hertz central frequency. But if I'm also looking at much shallower, the frequency content of the seismic up here would be higher because we haven't had as much attenuation. So I'd still use a minimum phase pulse, but instead of, say, 18 hertz down here, I might be using 23 or 25 hertz up here.
Great. We have a question from Nicholas, who asks, what scale is reasonable to extend your depth conversion in the horizontal direction between well control?
I think what I would tend to do is I would use the depth control that I have from check shots or VSPs calibrate that to the stacking velocities. Typically, stacking velocities run a little high. The rule of thumb that I'm aware of is oftentimes people use 90% of the stacking velocity if they don't have any local calibration with check shots or VSPs. And so I'd use my local calibration. I would figure out that the stacking velocities, let's say, are 92%, or using 92% of the stacking velocities ties to the VSP check shot data. Then I would use the velocity model using the factor of 92% to extend my depth predictions away from wells.
Great. Joanne Stock asks, if we have a longer section of well, how do we control the important sequence boundaries during the log seismic tie?
Yeah, usually when they're drilling the wells, the way they model where to stop one run and start another run, where they go from one diameter pipe to a slightly smaller diameter pipe, is usually controlled by pressures if it's going to be some overpressuring in the area. So typically a geoscientist does not have control over where an individual drilling segment and logging runs will be run. Hopefully your seismic sequence boundaries will still be able to be identified no matter where one run ends, another run begins. One of the things that you do have to be aware of is that when the logging for a run starts, sometimes the collar that connects the one diameter pipe to the next, that can cause some errors in your log measurements. And I still remember my first well seismic tie. I didn't understand what these metal collars were, and the raw sonic data had errors in it because it was measuring the velocity of the steel, and I wasn't smart enough at that point or experienced enough at that point to realize I had to edit those things out. So I had anomalous large peak or trough where the collar was, and once somebody explained to me what was going on and I did the editing, my well seismic tie looked a whole lot better. So a little bit of confession on my part.
Great. Someone just asked if you could just please go over the concept of the Ricker wavelet and seismic processing.
Okay. I think everyone knows, if you've taken exams and the test results are not fantastic, that you usually ask your professor, are you going to mark this test on a curve? And what that means is, are you going to fit a bell-shaped curve so that 67 becomes an A and 53 becomes a B and 38 becomes a D? So a bell-shaped curve is a normal distribution. So it's a specific shape for a distribution. A Ricker wavelet is a certain form for the distribution. And so that Ricker is something that I think was proposed back in the 30s, perhaps. And it seems to be a fairly widely used analytic shape for people that are doing well seismic ties.
Okay, great. How does the used seismic source, like dynamite or vibra-seis, affect the seismic to well tie?
The type of source that you use is something that the acquisition and the processing people will try to work together on, so that the type of source doesn't really impact the geologic information in your seismic section. So I have done well seismic ties with vibrator data, with dynamite data, and with airgun data. And usually the trouble or simplicity or complexity of doing the well seismic ties has not really varied with the type of energy source.
Great. If we have two or more reservoir positions and the well ties with the seismic at one but doesn't tie with the other position, what do you advise?
If they are at fairly different depths, I would be surprised if one synthetic would tie both of them. One of the limitations with the software I know of is that you can only specify a single wavelet, either an extracted wavelet or an analytic wavelet. And so what is commonly done is one synthetic with one wavelet would be used to tie the shallower zone of interest, second one for the intermediate depth, and a third one for the deeper depth. So it is permissible to use different synthetics with different wavelet characteristics to tie different portions of a fairly deep well.
Great. There's a question that says that they'd like to ask about like quantitative measure of a well tie quality. Which values of cross correlation would be acceptable for a well tie used in an inversion project? What would be an acceptable value for cases where you need to estimate either density or sonic logs? And if our seismic volume was post-stack migrated instead of pre-stack, could it have an impact on the well tie?
Okay, the first question about the cross correlation, I think different people would propose different minimum values, so to speak. One of the problems with the cross correlation is that you can get a high correlation without having the proper tie between the synthetic wiggles and the real wiggles. And so I, for one, am cautious about using a high cross correlation value to quantify how good the tie is, or if how I have positioned the synthetic is proper, as opposed to maybe moving it up a few milliseconds or moving it down. The second question, the seismic tie, well tie, is always going to be dependent on the data quality, both for the seismic and also for the well data. And so if you have post-stack migration, your imaging is never going to be as good as if you have a good pre-stack image section. And so I would expect the well seismic ties to be much improved if you are fortunate to have pre-stack time or pre-stack depth migrated data. Similarly, there can be things that is in the well data set that could cause problems. I mentioned the collar in my first well seismic tie was something that was erroneous, that needed to be edited. We could have washout zones, we could have fluid invasion zones. The check shot data can have problems. Somebody could have misinterpreted the first arrivals. And so you have to look at what you can do to improve the quality of both the well data and the seismic data if you want to get a better well seismic tie. Again, it depends on your business cycle, and if using the Barracuda Gippsland Basin data set as an example, if I just want to know where to carry the top of the Latrobe unconformity, I can live with a tie that's reasonably good in terms of matching up peaks and troughs. if I want to use quantitative seismic attributes to make predictions of net to gross or feet of pay, something like that, then not only would I want the peaks and troughs to line up, but I'd want the shapes of a peak and the shapes of a trough on the model data to match the real data. So we don't want to overwork our problem getting a superb well seismic tie when a fair to good seismic tie gives us our necessary information.
Great. How do you do the correction when you observe anomalies in your caliper log while doing QC?
Could you repeat that?
Sure. How do you do the correction when you observe anomalies in your, I think it's caliper log, while doing QC?
Yeah, the caliper log, we would monitor to see if there's a washout zone. And so if there's a washout zone, the log measurements over that zone would not be proper for the formation. And so typically what we will do is we'll extrapolate or interpolate in between the data prior to the, or shallower than the washout zone, to the data just below the washout zone.
Okay, great. If we do not have check shot, can sonic work? What other logs can we use?
If we don't have check shots or VSPs, then our zero time on the synthetic is not reliable. And so what we can do, let me flip here. We do have a couple of check shots for this particular well. So I can move the red curve, the synthetic curve, up maybe as many as 15 or 20 mils, down maybe 10 or 15 mils. If I did not have any check shots, then I might be able to move this synthetic up or down 100 or maybe even 200 milliseconds, depending on how the zero time on the synthetic has been established. So the check shot gives me some calibration. It gets me in the right zone, but I still have a little bit of wiggle room.
Great, thank you. There were a couple of other questions, but they're a little specific, and so I wanted to let those people who asked those questions that in the event that this happens, I download the questions for Fred and send them to him, and he can try to answer you directly. And so there's 2 additional questions like that, Fred. So okay. I will send that listing to you, and that way you can reply directly. And so with that said, that was a great Q&A time period today. And Fred, thank you so much. And we will see you next Tuesday for seismic acquisition. So thanks, everyone.
Okay, thanks, everyone, for your interest in the series. And talk to you next Tuesday.
All right, sounds good. See you then. Bye, everyone.
Okay, bye-bye.